So hi, my name is Farah Akila binti Muhammad Dewana and I'm from RK93 Computer Network Engineering. So I would like to give you guys some information for our mini project, an automatic anesthesia control system for EKT318 modern control system. So in this group there are 4 members. First, Seva anak lelaki Bad Manatan. Second, Muhammad Amirul Mukminin. Third, Syazwani Yuzwani Amir. And fourth is me. So let's start.
For the introduction, anesthesia is a state of controlled temporary loss of sensation or awareness that is induced for medical purpose. Anesthesia enables the painless performance of medical procedures that will otherwise cause severe or intolerable pain to an unanesthetized patient. There are 3 main types of anesthesia. First is local, numbs or one small area of the body. You stay awake and alert. Regional is block pain in an area of the body, such as arm or leg. Generals make you unconscious. You do not feel any pain and you do not remember the procedure afterwards. So, we move forward to problem statement. Cause of the pain from anesthesia. The pain is imprinted on many people's memory so that they postpone actual treatment because of their fear of anesthesia, even though they have a disease which required a treatment. The pain from anesthesia is the pain generated during an actual anesthesia is caused by the speed and amount of injection of anesthesia solution. But most widespread anesthesia devices do not have a function to control them. So, for the solution, effort of medical committee for reducing pain from anesthesia is, in order to overcome the technical limit of the conventional anesthetic device, the related medical teams and research came to devise a system to excellently control the speed and amount of injection of anesthetic solution, which are the fundamental cause for the pain from anesthesia. So, for the aim of the system that was given to us is to maintain the steady intake of drug with regard to the suitability of each patient. Second, to reduce the amount of relaxant drug consumed by the patient.
Assalamualaikum warahmatullahi wabarakatuh. Saya Muhammad Amirul Mukminin bin Kamar Zaman from group Automatic Anesthesia Control System. Today I can present to my part. Objective: to determine the gain and pace margin of the system, to design a compensator that has pace margin at least 50 degrees. Methodology: this project was performed using Scilab software. The transfer function of this system can be calculated by cascading both of the GS function in the given system. The value of K is substituted with K equal 3 as given in the question. The value of the numerator and denominator, which is obtained from the transfer function, is fed into the Scilab software to plot the BODE plot and require the gain and pace margin of the system. The new gain crossover is determined from the graph. Alpha is calculated. Thus, the value is substituted in the Scilab to confirm the phase margin, which should be at least 15 degrees.
Hi, my name is Jiva Padmanathan from RK93 Computer Network Engineering. Today, I'm going to explain about question part in our task, that is automatic anesthesia control system. This is the question for automatic anesthesia control. In this figure, you can see that there are an input of RS that known as design relaxation level, and YS is known as the actual relaxation level, and also have a controller, and it was indicative control system. So the part 1 for the system is to draw the BODE plot of the system and determine the gain and phase margin of the system, and we need to assume K equals to 3. And part B is you are required to design compensator, lead or lag, so that the phase margin will be at least 50 degree by producing your design using Scilab of the system. Now it's a solution for part A, which is K equals to 3. This has been substituted in the equation below as shown in the screen. So the transfer function given was K over 0.3 s plus 1 multiply with 1 over s 0.6 s plus 1. We need to substitute K equals to 3 into the equation. So the transfer function will be 3 over 0.3 s plus 1 multiply 1 over s 0.6 plus 1 n equals to 3 over s 0.3 s plus 1 multiply 0.6 s plus 1. The values of the transfer function is solved, and which obtained from the above is inserted in the Scilab to generate the BODE plot and determine the gain and phase margin of the system. This is the BODE plot of our system. From Scilab we obtain BODE plot graph as shown. This is the original system without a compensator, that we obtain the phase margin of 14.54 degree and gain margin of 4.44 dB. Next, from the BODE plot we can know that the phase margin is 14.54 degree and gain margin is 4.44 dB, but the requirement needed at least of 50 degree phase margin. So therefore we need to design a 55 degree phase lag network by account 5 degree of safety margin by add 50 plus 5 degree to get the 55 degree of compensator level. As you can see from the code, we know that we have 14.5370003346311753 phase margin, and after we round off we get 14.54 degree of phase margin, and also gain margin from the code we get 4.4369749923271222. So we rounded off that value into 4.44 dB.
Hi, Assalamualaikum and a very good evening. My name is Shazwani binti Yazani Amer. I am from RK93 and my matric number is 1712327880. The next part in task 5 is that we are required to design a compensator lead or lag so that the phase margin will be at least 50 degree, and we are using Scilab to design this system. First thing first, we need to find the frequency phase for the system. We added 5 degree to the phase margin required as safety margin. So negative 180 plus 55 degree, thus we get our frequency phase, which is negative 125. And then by using Scilab, the gain crossover frequency omega c that we have obtained is 0.1127 Hz or equal to 0.708 radian per second. Next, we need to find the gain at omega c. The omega c that we have obtained earlier is 0.708 radian per second. So, by using Scilab, the gain that we have obtained at 0.708 radian per second is 11.63 dB, which is also equals to 20 log alpha. Alpha is decay. And here we have our alpha value, which is equal to 3.815. Next, we need to rewrite the phase lag network transfer function GCS, which is equals to 1 plus tau s over 1 plus alpha tau s. In order to rewrite this, we need the value of tau. So to find the tau, we are going to be using the formula of 1 over z. To find the z, z is equals to omega c over 10. By using the omega c value that we have obtained earlier, which is 0.708 divided by 10, then we get our z value, which is 0.0708. Substituting into the tau formula, which is 1 over z, and then we get the value of tau, which is 14.12. Then only we can substitute the value of tau and alpha into the GCS formula, and then only we obtain our phase lag network transfer function, which is 1 plus 14.12 second over 1 plus 53.92 second. And now we are going to design the compensator that has phase margin of at least 50 degree by using Scilab. This is the coding. First, we are going to insert S equals to percentage S to define the system. And then we are going to insert the num value, the den value, the num C value, and the den C value in order to insert our gain formula, which is G equals to num C over den C multiplied by num over den. Then we insert num value, den value, num C, and the den C value that we have obtained earlier. And then here is the transfer function that we have obtained. And next, this is the graph for both phase and magnitude that we obtained from the Scilab.
Next. Conclusion. Based on our observation, this system is stable. In order to determine the system is stable or not, we can use BODE plot and lead lag network. We use Scilab to obtain the BODE plot of the system, which is known as gain and phase margin. Thank you.